Hey everybody, it's Thursday, December 10th, and as you can see here in the aim today, our goal for today's video is to pick right back up where we left off yesterday. So if you remember back to yesterday's video, yesterday we introduced Kepler's laws of planetary motion. And as we mentioned yesterday, there are three laws of planetary motion as described by Johannes Kepler. Yesterday, we discussed the first two of those three laws, and today, as I mentioned at the end of yesterday's video, we are going to dig into the third law. The third law is a little bit different than the first two because it's the only one that's actually given by an equation, and because I figured it would take us a little while to get comfortable with that equation, we might as well save it and make that one single video. And so that's what we're going to do here for today. Before we get into that, though, real quick, I just want to take a couple of minutes to summarize the first and second law before we get into the third law. And so if you remember back from yesterday, we said Kepler's first law of planetary motion says the path of each planet is an ellipse with the sun at one focus. And so the basic idea here is that this law simply describes how planets move when they are in orbit around the sun. Now, as it turns out, this is not just true for planets orbiting the sun. So, like, it's not just true for the solar system. It's really true for any object in orbit around any other object. Now, we said yesterday the reason why this is true is because Newton's universal law of gravitation is what we refer to as an inverse square law, meaning the force is larger the closer you get to the sun or to the object you're orbiting, and the force is smaller the farther you get, and that it's inversely proportional to the distance squared. That's why it's called an inverse square law. But the basic reason here is not that important. You just need to know that the planet follows the path of an ellipse. Now, the reason why the reason isn't important is because we do not have the knowledge base yet to prove that it is the nature of the inverse square law that is the reason for this law. And so what you will see, as I think I mentioned in great detail yesterday, is that as we continue to move through the year and gain more knowledge, we are going to come back and revisit these laws so we can sort of gain a greater understanding of them and see how Kepler's laws fits into the larger picture of the course. And so stay tuned on that. Really, what you need to know for now is the planets move in elliptical orbits. Kepler's second law of planetary motion is a little more complicated. It says that each planet moves so that an imaginary line drawn from the planet to the sun sweeps out equal areas in equal times. This is referred to as the law of equal areas. And so essentially, while this law looks more complicated than it actually is, essentially what this law is saying is that when the planet, like the planet pictured in this diagram, is moving from C to D, it's going faster than it is from A to B. It goes faster when it's closer to the sun and slower when it's farther away from the sun. And the way that we reason that through is because the force of gravity is an inverse square law. And so because C to D are closer to the sun, the force of gravity is larger there. And so as the planet swings around from B to C, it's getting closer to the sun. The sun is exerting a larger force on the planet as it gets closer and closer. And because the force has a component which is in the direction of motion, it causes the planet to speed up. Additionally, we can say that when the planet is going from D to A, the force of gravity is getting smaller and smaller and smaller. And not only is it getting smaller and smaller and smaller, it also has a component which is directed opposite the direction of motion. And so because the force of gravity is opposite the direction of the planet's velocity, the planet will slow down. Now, it's not going to slow down to a stop or anything. And that's because the force is actually just going to get smaller and smaller and smaller as it moves away. But that's the idea. the areas are equal because it's moving faster here than it is here. And right now, we can say that's true because of the inverse square law. I believe I mentioned yesterday that the reason why this is true is really because of a law of physics, which we have not covered yet, called conservation of angular momentum. Now, we haven't gotten to that yet, so I'm never going to expect you to explain that. But again, when we get to conservation of angular momentum, we will loop back around to Kepler's laws. We will actually derive the law for equal areas, so you will see how it works. I think it's important to realize, though, whether we are talking about the law of equal areas from the perspective of Newton's universal law of gravitation, from conservation of energy, or conservation of angular momentum, or basic just kinematics about the velocity and the acceleration being in the same direction or opposite directions, we all those explanations lead to the same answer, which is that it's going faster from C to D than it is from A to B. That's the deal. So the first law describes the shape of their orbit. The second law describes the velocity, essentially, of this object when it's in orbit. The third law is totally different. And there's no point in beating around the bush, so let's just get into it. Kepler's third law says the ratio of the squares of the periods of any two planets revolving around the sun is equal to the ratio of the cubes of their mean distances from the sun. The ratio of the squares of the periods is equal to the ratio of the cubes of their mean distances. It's a lot. Having said that, before we actually write down the equation, I think it is important to just take a second to realize Kepler was dealing with handwritten data collected in a painstaking way. And it's important to realize how much of a labor it truly was to be able to sift through all of that data without a calculator, mind you, to realize that if you take the periods and you square them, and then you take the mean distances from the sun and you cube them and then you divide them, that number is equal. That's pretty wild to be able to figure out in like the early 1600s. And yet he was able to do it. It's not, it doesn't take like a real genius to be able to do that. I think it's important to realize it just takes hard work. These were, for the most part, regular people. And they just worked hard at it and came to discover these fundamental truths, which is pretty cool. And so to write down this law, which is written here in words, as an equation, it's actually not that tough. It says the ratio of the squares of the periods. So we'll just label them 1 and 2 to differentiate them. The ratio of the squares of the periods is equal to the ratio of the cubes of the distances. That's it. Now, you can rearrange that whichever way you want to solve for whichever variable you have to solve for. And so let's just go ahead and write down here, T1 is the orbital period for planet 1. T2 is the orbital period for planet 2. R1 is the mean distance from the sun for planet number 1. And I'm going to write in parentheses here from sun, although I'm going to clarify that in a second. And then R2 here is the mean distance for planet 2. And I'm going to write in parentheses again from sun. Now, there are a couple of points here, because you guys know how to use equations. You're smart. It's not that complicated. I think I want to clarify a couple of points, though, to make sure we're all on the same page. The first point is orbital period is a measurement of time. And so I'm going to write seconds here. But I think it's important to realize these are ratios. So the only real requirement is that these need to be the same unit. Ideally, we would put them in the standard metric unit. But if you had the period for one planet in hours, it's just that this equation is going to spit out the period for the other planet in hours if that's what you're solving for. If you're solving for one of the distances, then you need to put the units in as the same thing. I think that's the basic idea, and I'd imagine a lot of you, basically all of you, are not going to be confused by that. This is a ratio. It's essentially sort of like a unitless equation. T1 squared divided by T2 squared is going to have units that cancel, or it should, at least, is the point. And so I'm going to write seconds here, but it's important to realize it doesn't really matter just as long as you use the same unit for the T's and the same unit for the R's. And I think the obvious point here is that you're going to have 3 of these 4 variables and have to solve for another one. So let's just say you have to solve for R1. Well, you're going to have T1 squared over T2 squared. Those units need to cancel, so it should be the same unit. And then you're going to move R2 cubed over here to the left-hand side of the equation. And so the basic idea is whatever unit you plug in for R2, well, then the equation is going to give you that unit for R1. Same thing over here. If we were solving for T1, we would have R1 cubed over R2 cubed. Those units should cancel. And then when we move T2 squared to the other side, whatever unit that has, T1 is going to have, because the equation is just going to spit out that unit. And so I'm going to write here meters for the R's, but the point here is it needs to have the same unit. Now, I want to comment very quickly on one thing before we move on. It's important to realize in various textbooks, you'll see this written in slightly different ways. So like up here on this planetary data sheet I gave you, this particular textbook has this law given with S's for the mean distance from the sun. I think that's kind of silly since the gravity equation already uses R's. And so I'm going to write it in terms of R's, but I want you to realize that if you wrote it in terms of S's, that's fine if you want. Now, moving on, there's not a whole lot going on here, but we do have one more point to make. Kepler's third law is always written by saying, basically it's always written how I wrote it here. The ratio of the squares of the periods for any 2 planets revolving around the sun. The point that I'm trying to make is this does not just apply to planets orbiting around the sun in the solar system. Kepler's third law actually applies to any 2 objects orbiting a common object. So for example, the ratio of the squares of the periods of the moon and the International Space Station is equal to the ratio of the square of the cubes from the mean distance of the moon and the space station to the Earth, because they orbit a common object, the Earth. And so that's the point here. So like you could do this for moons of Jupiter or whatever, just as long as the 2 objects orbit the same thing, this equation will work. And so let's write that down. This is not just true for planets/objects, plural, orbiting the sun, but for any 2 objects orbiting around the same object. That's a crucial point. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So I want to just make a quick point here that you can rearrange this equation. I don't want you to write this down just now, but it's important to realize you can rearrange this equation basically by switching these 2 variables, let's say. So instead of keeping the T's on one side and the R's on another side, let's keep the 1's on one side of the equation and the 2's on the other side of the equation. If you do that, you get T1 squared over R cubed equals T2 squared over R cubed. And so it's important to realize a consequence of this equation is that not only are the ratio of the squares of the periods equal to the ratio of the cubes of the distances, it's also true that for any object orbiting, some common object, for any of the objects orbiting some common object, T1 squared over R cubed is going to be a constant. Because, let's just say we're talking about the planets in the solar system. For any of those planets, these have got to be equal. So that means for any planet, T1 squared over r cubed is going to be the same number. Now, of course, the question is, what is the significance of that number? I cannot tell you that yet, or I can tell you that, but I can't tell you why it's equal to the thing it's equal to yet. That's actually the first thing we're going to do. Next week, we're going to start it. It's going to be circular motion. And by the end of the circular motion unit, we will revisit this and talk about why this next equation that we're going to look at is true. But it's also important to realize there is a second version of Kepler's third law. And that second version of Kepler's third law looks like this. T squared equals 4 pi squared r cubed over gm, where t is the orbital period for orbiting object, and that's going to be measured in seconds. We have our r here, which is the mean distance from the sun, or mean distance from the orbited object. Of course, g is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. And m here is going to be the mass of the object being orbited, which of course is going to be measured in kilograms, where the mean distance is going to be measured in meters. And so the basic idea here is that because, notice, we can solve this equation if we take this r cubed and move it across the equal sign into the denominator, we would have t squared. I'll just write this over here. You can write it too. T squared over r cubed is going to be equal to 4 pi squared gm. And notice 4 is a constant, pi squared is a constant, g is a constant, and the mass of any planet or like the sun or whatever is a constant. And so the reason why t squared over r cubed is the same for all planets in the solar system is because all of those things that t squared over r cubed is equal to is constant. That's the idea. And so what I want to do here for the rest of this video is just use these equations, the two versions of Kepler's law, version 1 and version 2, and I'll even go ahead and write over here like this is version 2, to solve some problems. The first one is located in the gravity packet on page 6, number 57. It says Neptune is an average distance of 4.5 times 10 to the 9 kilometers from the sun. Estimate the length of the Neptunian year, given that the Earth is 1.5 times 10 to the 8 kilometers from the sun on the average. And so notice here, they're giving us the distance for Neptune, and they're giving us the distance for Earth. Now, it doesn't really matter which one you call 1 or 2, just as long as you realize that whichever one you call R1, T1 has to correspond to that, and that T2 would have to correspond to whichever distance you call R2. Generally, what I do is whichever one is listed first in the problem, that's the one I call number 1, and so that's what I'm going to do here. So Neptune is an average distance of 4.5 times 10 to the 9 kilometers from the sun. So I'm going to write here R1 is 4.5 times 10 to the 9 kilometers from the sun. R2, then this is for the Earth now, as it says in the problem, is 1.5 times 10 to the 8 kilometers. And I know it said 1.50, but since this is given to 2 sig figs, that third sig fig is not even really going to matter. And so I'm just going to go ahead and call this to 2 sig figs. And now it's important to realize what they're asking you for is the length of the Neptunian year. And so that's going to be T1 is what we're looking for. And so the only other thing we have to know is the orbital period for the Earth. Does anybody know the orbital period of the Earth off the top of their head? I don't know what it is. I could figure it out in seconds. But the point is, you don't need to figure it out in seconds. Just as long as you realize that whichever unit you use for the period of the Earth, T2, that's the unit you're going to get for T1. And so what I'm going to do, just to make my life easy, is say the period is 1 year. That's it. Notice 1 is an easy number to square. And if I really need it in seconds afterwards, well, I could just take my answer in years and convert that to seconds. And so we're in business. Looking at this problem, notice here, this is a question where we just need to use the first version of Kepler's third law. And so that'd be T1 squared over T2 squared equals R1 cubed over R2 cubed. And so to solve this for T1 is pretty easy. We have T1 equals T2 squared. Notice we're moving that up and over, times R1 cubed over R2 cubed. And of course, because the T1 was squared, all of that needs to be under the radical. And so basically this reduces to a fairly straightforward plug-in. T2 squared is 1 year. You got to square that. Times R1 cubed. So that's going to be 4.5 times 10 to the 9 kilometers cubed. And then divided by R2 cubed, which is 1.5 times 10 to the 8 kilometers cubed. Now remember, the kilometers cubed, they're going to cancel. And so all I have left over with under the radical is year squared. And when I take the square root of that, it's just going to give me years. And when you do that math, 4.5 times 10 to the 9 cubed divided by 1.58 cubed, you get 2,700. Or excuse me, 27,000. You multiply that by 1 squared, and of course that's still 27,000. And then you take the square root, and you get 164.3 years, or to 2 sig figs, 160 years. And of course, these are Earth years. But generally, every time we report something in years, everybody knows we mean Earth years, but just to be specific. And so that's it. That's Kepler's third law. Now, of course, it'd be nice to know if that was correct. And we can use this reference sheet to check. Because this chart from that textbook has these numbers. And the Neptunian year, according to this chart, is about 165 Earth years. And looking at our number, we got 164.316, and we're right on the money. Now, notice we didn't get the exact same number, 165, because we rounded that off to 4.5 times 10 to the 6 kilometer, or 4.5 times 10 to the 9 kilometers, and we rounded this to 1.5 times 10 to the 8 kilometers, but, you know, the rounding makes our answer a little different, but other than that, we're right on the money. Notice what I like about this chart also is it shows you the ratio of, instead of doing t squared over r cubed, it does r cubed, or in this case, s cubed over t squared. But notice, more or less all in agreement. Slightly different. You can see here that Mars is a little different and the Earth is a little different from like Saturn and Mercury, but just about there. Remember, we said Kepler's also not perfect because they do not account for the gravitational interactions between the planets, but it's close. And that's pretty cool. I want you to try one of these on your own. This one I think is a little more difficult. It says here the asteroid Icarus, this of course is in the gravity packet on page 6, number 58. It says the asteroid Icarus, though only a few hundred meters across, orbits the sun like the planets. I showed you that in that picture yesterday. That was one of the asteroids shown in the pictures for Kepler's First Law. It says that its period is 410 days. What is the mean distance from the sun? Now, it's important for everybody to realize that it doesn't really matter what you use. Notice they only tell you things about Icarus. And so the hint I'll give you is we're saying the ratios of the periods are, the ratio of the periods squared are equal to the ratio of the distances cubed for two things that are orbiting the sun. So it should be clear to everybody that you have to use something else that's orbiting the sun. Use an easy one that you know, or, one that you live on. Take a second to pause this video here and perform this calculation. Be very careful with the calculator. And when you hit play, we'll go over it. So the first thing I need to do here is I need to write down my knowns. And the only known they give me is that the period of this asteroid Icarus is 410 days. And for no reason other than that's just what I'm going to do, I'm going to call that T1, 410 days. I might as well just write days. That means whenever I find this distance, that's going to be R1. And so I need T2 and I need R2. Don't be silly. You don't need to look up what the period of the Earth is in days. It's 365 days. Now, of course, generally there's one kid in the class every year who raises their hand and says like, actually the period of the Earth is 365.25 days. Why aren't we using that? It's because we're not actually performing very delicate calculations here. We're only doing these things. Notice 410 days is only given to 2 sig figs, so we don't really care. It's not going to make that big of a difference. It is true that the orbital period of the Earth is 365.25 days. If you never realized that, it's why we have a leap year every 4 years, because a quarter of a day for 4 years makes a whole day. But that's the idea. And now we just need the orbital radius of the Earth, but they told us that in the last problem is 1.5 times 10 to the 8 kilometers. And so we'll use this as 1.5 times 10 to the 8 kilometers, which is not a problem, just as long as we recognize we're going to get kilometers out in our answer. Now, actually, I'd like to go back and change something here. What I'd like to do is I would like to actually go ahead and say that number was a little off. Let's use this one, the mean distance. So we'll do 1.496. Just for kicks here, we'll say 1.496 times 10 to the 8 kilometers. Whichever one you use, though, doesn't really matter. It's going to be close enough, I'm sure. So we have T1 squared over T2 squared equals R1 cubed over R2 cubed. And we're looking for R1. So that means we're going to have R1 is equal to T1 squared times R2 cubed over T2 squared cube root. And so plugging in these numbers here, it's very important to remind yourself to always write that 3 for the cube root every time you are doing this, because it's not a square root, it's cube root. We have here 410 days, T1. We got to square that. And then we're going to multiply that by R2 cubed. So that's 1.496 times 10 to the 8 kilometers. And we got to cube that. And then we're going to divide that by 365 days squared. And so now we go to the calculator. I want to show you this because I think this is important, because I notice a lot of kids getting this wrong every year. So we take our 410 days and we square it and we get a big number. And we have to multiply that by 1.496 times 10 to the 8 cubed. And so I just do the caret 3. There's no point in going through the menu. Then, so notice we have a huge number here. Then I need to divide this by T2 squared. So I'm going to divide that by 365 squared. And I get another ridiculous number. And now I need to cube this. Now, it's important to realize when you are, or sorry, I just said cube this. You have to take the cube root of this. It's important to realize when you need to take the cube root of something, you can do it a few ways. You can go to math and then do it that way. Honestly, I don't usually do it like that. It's important to realize when you're taking a square root is the same as raising the number to the 1/2 power. I would imagine that's something maybe you know already. And when you take a cube root, it's the same thing as raising the thing to the 1/3 power. And so, because I don't feel like clicking too many buttons, usually what I do is I just hit answer to the 1/3 power, and then I'm done. And when I do that, I get a disgusting number here, 1.6, and then it's 1, 2, 3, 4, 5, 6, 7, 8. So 1.62, we can call it 1.62 times 10 to the 8 kilometers. And so notice, it's got a pretty similar orbital radius to the Earth, but it's got a pretty similar orbital period to the Earth too, so that follows. Notice T1 over T2, and squaring both of them, 410 squared over 365 squared, is only 1.26. So it would make sense that because the period is only 1.26 times bigger, or the period squared is only 1.26 times bigger, then the cube distance for Icarus is only going to be 1.26 times bigger than the cube distance for the Earth. And so if we were to Google that, just to make sure it's right, it's hard to find on the internet, actually. You have to find it on Wikipedia. And if you look at Wikipedia, notice, in order to be able to figure this out, you actually have to know some stuff. Because notice, it does not say mean distance to the sun. What it does say, though, is the semi-major axis. What you should know, as we mentioned yesterday, is that the semi-major axis length is the distance, the mean distance from the sun. And so the basic idea here is that it says here the semi-major axis is 1.0781 astronomical units, and an astronomical unit is defined as the distance between the Earth and the sun. And so if we take 150 million kilometers and we multiply it by 1.0781, then sure enough, we get our answer to this question, 1.62 times 10 to the 8 kilometers. To finish us up for today, I want to look at one more problem. And the one more problem is calculating the mass of the sun. It says here, using the planetary data for any planet, I want you to use the second version of Kepler's third law to calculate the mass of the sun. A lot of kids always ask me when we do that first gravity problem that we did like a couple of weeks ago, or not a couple of weeks ago, whatever, last week, when we used the mass of the sun to calculate the force of gravity between the Earth and the sun. A lot of people always ask me, how do we know the mass of the sun? Like, obviously, we didn't just weigh it. This is how we know the mass of the sun. That's pretty wild. The sun is 93 million miles away. And we know how much mass it has because we can look at objects, including the object we are on, as they orbit it. If you don't appreciate that, then there's something wrong with you, I think. So for this one, notice in this equation, the mass of the object being orbited in this problem is the sun. And so I'd like you to use this equation using the square of the mean orbital distance, or excuse me, the cube of the mean orbital distance and the square of the period to calculate the mass of the sun. And you can do that with any planet, your favorite planet, your least favorite planet, anyone, doesn't matter. Take a second to pause this video here. Go ahead and use that equation to calculate the mass of the sun. And when you're finished, hit play and we'll go over it. Okay, so it should be clear to everybody that you have to use the planetary data reference table. And this table is really the only one that works well for you because it's the only one that gives you the period in seconds and the mean distance to the sun in meters. And so, since I told you you could use any object orbiting the sun here, I'm imagining that we're not all going to use the same numbers here. And so I'm going to skip the part where I write down knowns and unknowns just to make this go quicker, although it should be clear to everybody that according to this equation, the knowns would have to be R and T and G. The rest is just 4 and pi squared, so it doesn't matter. And so I'm going to go ahead and use Jupiter. Jupiter, the big one, might as well. We have here for Jupiter that its orbital period is 3.74 times 10 to the 8 seconds, and the mean distance from the sun is 7.78 times 10 to the 11 meters. It's big and it's far. And so we'll use that to calculate the mass of the sun because Jupiter orbits the sun. And so the equation that we wrote there on that slide is t squared equals 4 pi squared r cubed over g m. And so that means m, the mass of the sun, is 4 pi squared r cubed over g t squared. And so plugging in our numbers here, we have 4 pi squared times the distance, which we said looking in that table was 7.78 times 10 to the 11 meters. And we got to cube that. And then we're going to divide that by g, which is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. And then we have to multiply that by t squared, and we said the period was 3.74 times 10 to the 8 seconds. And when you do that math and you plug in those numbers, 4 times pi squared times 7.78 times 10 to the negative times 10 to the positive 11 meters, and then you cube that, just the r, and then you divide that by g times t squared, 6.67 times 10 to the negative 11 times 3.74 times 10 to the 8 seconds squared, you end up getting 1.99 times 10 to the 30 kilograms, which is, in fact, the mass of the sun. Pretty cool. Now, I'm hoping what you're recognizing is that that's pretty cool because you just used a planet that was not Jupiter and I just used a planet that was Jupiter and we got the same number. But if you're not convinced, let's just go ahead and do this for one more planet. And so we'll write here the unknown is the mass. We have here our equation, t squared equals 4 pi squared r cubed over g times m. And so that means m is going to be 4 pi squared r cubed over gt squared. And so that means the mass is going to be 4 pi squared times the r of the planet we choose over g, 6.67 times 10 to the negative 11 meters cubed per kilogram second squared, times the period of whatever planet we're going to choose squared. And we picked Jupiter, so let's go ahead and pick the smallest one. We have Mercury with a mean distance from the sun of 5.79 times 10 to the 10 meters and a period of 7.60 times 10 to the 6 seconds. And so we're going to plug in here our mean distance from the sun, which is 5.79 times 10 to the 10 meters, and our period, 7.60 times 10 to the 6. And when you do that math, taking 4 times pi squared times 4.79 times 10 to the 10 meters cubed, and then divide that by the product of 6.67 times 10 to the negative 11 and 7.60 times 10 to the 6 seconds, you get 1.989, or to 3 sig figs, 1.99 times 10 to the 30 kilograms. It works regardless of the planet you use in the solar system. And that is how we know the mass of the sun. And that's pretty cool. Thanks, Kepler. And with that problem, that is it for today. The test on projectile motion is tomorrow. And we will have a meeting about that tomorrow, and then you will take the test. Good luck, everybody. Take care.